In Chapter 5, we derive the equations of elasticity. That's the response of a solid body to applied forces on the boundary or the interior. And there, recall that we basically our equations came from saying that the density, mass per unit volume, times the acceleration, which was displacement, second derivative of the displacement with respect to time, is equal to, and then we put the forces, the internal forces and the external forces. We had an external force vector due to gravity or whatever, and then there were the forces that the rest of the material applied to a given piece of the solid. Well, in this chapter we're looking at fluids now, liquids basically, because it's going to be incompressible fluids. So this chapter we're talking about liquids, not gases, not solids. And we're going to do the same kind of analysis, except now we're going to, instead of looking at a little stationary piece of the solid, we're going to look at a moving piece of the fluid. So let's, if we have a little piece S of fluid that's moving with the fluid, and let's say that the parametric equations of that small body are x of t, y of t, z of t, and UVW is the fluid velocity field, which depends not only on time but the position of that particle. Then the derivative of the velocity, that would be the acceleration of that moving piece. Use the chain rule and you get u sub x times x prime plus u sub y times y prime plus u sub z times z prime plus u sub t, which is exactly this, because x prime is u, y prime is v, z prime is w. That's the velocity. The velocity vector UVW is just equal to x prime comma y prime z prime. So that is the acceleration of a moving piece, a piece of the fluid that's moving with the fluid. And the right-hand side are the forces acting on that moving piece. They're the external forces and then the internal forces. And we end up with basically this looks exactly like it did in Chapter 5, except now the stresses are different. Actually, the shear stresses are almost the same. And we're not going to try to derive these or justify these at all, but this stress tensor in terms of the, well, now u and v and w are not displacements, they're velocity, but they involve the derivatives of the velocity and something called the pressure here. So we're not going to try to justify where these formulas came from, but if you take those formulas and plug it into this, you'll get the equations for an incompressible fluid, the Navier-Stokes equations. And if you simplify them by actually taking the x, y, and z derivatives of these things and simplify it, you'll get the following equations. The left-hand sides are exactly the same as what I showed you a minute ago. And then the right-hand side, well, you still got the external force vector, but then the stresses, the derivative of the stresses, after simplifying, looks like that. But now you've got a fourth equation here, which is called the divergence equation, u sub x plus v sub y plus w sub z equals 0. That comes from the fact that the fluid is incompressible, and that at least we can derive. Let's see where this formula comes from. So we go back to the derivation of the diffusion convection equation in Chapter 3. It was this is diffusion, that's convection. If there's an external velocity field v, that's sources. In Chapter 3 we call the density, we called it C, but here we're calling it rho. Rho is the density of the fluid, and we're assuming no diffusion, so and no sources or sinks. So basically all we have is convection. So this is the convection equation. The density of a fluid satisfies this, where V is the fluid velocity field. Now if you expand this divergence out, See, right now we're not assuming that density is constant. This is density is assumed to be a function of x, y, z, and t now, just like in chapter 3. We haven't assumed that it's incompressible fluid yet. This is, even if it's compressible, this will be satisfied. So this is basically the convection equation from chapter 3 with an external velocity field v and no sources and no diffusion. So you expand that out and you get, well, divergence means derivative with respect to x of the first component. Well, the velocity field now is UVW. That's the fluid velocity. This fluid is moving with the fluid. We're talking about the density of the fluid, but it's moving with the fluid with velocity u, v, and w. So v is the velocity, is the field, capital U, capital V, capital W. So we multiply that by rho and take the divergence. You get the derivative with respect to x of rho u plus derivative with respect to y of rho v plus derivative with respect to z of rho w. Then you expand those out using the product rule, and you get this. Now these first 4 terms are exactly the rate of change of the density of the moving piece of fluid, because the density is a function of position and time, but if we're looking at a moving piece of the fluid, the position is x of t, y of t, z of t. So if you take the derivative of that moving piece, we'll call that rho sub 0. Rho sub 0 stands for the density of the moving piece. See, rho is a function of x, y, z, and t, but if we look at a moving piece where x, y, and z are given functions of t, time, then the derivative of that with respect to time, rho sub 0 with respect to time, would be, again using the chain rule, it would be rho sub t plus rho sub x times x prime plus rho sub y times y prime plus rho sub z times z prime. And since x prime is just u, y prime is v, z prime is w, you get exactly that. So this thing right here is what's 0. That's the derivative of the density of a moving piece of the fluid. If it's an incompressible fluid, that is 0. Rho sub t may not be 0 because the fluid, that's the derivative of density at a fixed point in the fluid, and that might be changing just because different fluids with different density are moving in. But if you follow a piece of the fluid, its density is constant if it's an incompressible fluid like liquid, which means that this thing is 0. And that, remember, is the first 4 terms of this equation. So these first 4 terms represent the rate of change of density of a moving piece of fluid. Therefore, and that's 0, therefore this is 0, therefore ux plus vy plus w sub z equals 0. So that's where the divergence equation comes from for a incompressible fluid. But now it's important to think about the case where you have a fluid that's almost incompressible, but not quite. In fact, a real liquid will not be exactly incompressible, so let's suppose it's almost incompressible. What does that mean? That means that the relative change in the density of the moving piece of fluid divided by it, so that would be the derivative with respect to time of rho 0 over rho 0. That's the relative change in density. That's going to be almost 0, but in a real fluid it's going to be the pressure divided by some large number, because a big increase in pressure is going to make a small change in the density of the fluid. So that means that P over alpha can be set equal to this, where alpha is a large number. That means that that's what happens if you have a nearly incompressible fluid, that rho 0 is not exactly 0, but it's the pressure divided by a large number. And if you use that equation, divide this by P0, that means that pressure over alpha is equal to minus this, so the pressure is equal to alpha times that. Now that's important equation where alpha is a large number. So you see if alpha is large, that means it's almost incompressible. Ux plus Vy plus Wx is almost zero. A small change in the volume is going to make a large change in pressure, or a large change in pressure makes a small change in volume. And that formula is going to be very useful for the penalty method. So an almost incompressible fluid will not quite satisfy the divergence equation. It'll satisfy this. Okay, so these are the Navier-Stokes equations. There's 4 equations. This is the divergence equation that basically says the fluid is incompressible. This is what you get by setting the density times the acceleration equal to the force field acting on it. But now, if you try to solve this system of equations in 2 or 3 dimensions directly as written, you'll not have much luck with either collocation or Galerkin method or most any method. Just brute force try and solve this. It's almost impossible. So we're going to have to develop a trick, and there are 2 tricks we're going to use. And the first one will work for 2 or 3 dimensional flow, so let's talk about it first. It's called the penalty method, and that's what we just got through talking about. Basically, we use the equation that I just showed you here, that we just replace the pressure by minus a large number times Ux plus Vy times W sub z. So the pressure here, here, and here we just replace by minus alpha times Ux plus Vy plus Wz, and that gets rid of this last equation also, because if alpha is a large number, that is equal to the pressure over alpha, so it's essentially almost zero, so it's nearly incompressible. So this solves 2 problems at once. Basically, one of the main problems with these equations is that pressure here, first derivatives of pressure. There's no boundary conditions on pressure. The pressure is really the problem, and it gets rid of this equation. So this is called the penalty method, and it's basically just backing off a little and saying, well, the fluid's not quite incompressible, but it's almost incompressible. So you replace pressure by minus alpha times Ux plus Vy plus Wz. By the way, it still works if you make that plus alpha. But so that gets rid of the pressure and the 4th equation, and then we have just the 3 equations for U, V, and W. That's called the penalty method. So the penalty method works in 2 or 3 dimensions. Let's do an example using the penalty method in 2 dimensions. And there, if you simplify the 3D equations, remember this is one form of the 3D Navier-Stokes equations, where the sigmas are these, and you can reduce this to 2 dimensions pretty easily. You just get rid of the W equation and the Z derivatives and the W here. And it's pretty obvious changes. Just assume W is 0, and so there's no flow in the W direction, and the derivative of everything with respect to Z is 0, and it reduces to these. These are the 2D equations, and there's the 2D divergence equation. There's no W sub Z. And the penalty method, we just replace the pressure here and here by minus alpha times Ux plus Vy, and that gets rid of this equation, because if alpha is a large number, then that almost makes Ux plus Vy equal to 0, and gets rid of the pressure here, and we'll have 2 equations for U and V, and it all works nicely. We're going to solve the steady state equations. That means that U sub t and V sub t are 0. In other words, we go long enough in time to where U and V quit changing. Doesn't mean the velocity is 0, just means the velocity at any given point is constant. So steady state, the U sub t and V sub t terms are 0. These don't disappear, by the way, so it's still a nonlinear. The steady state equations are nonlinear because, see, the U times Ux and V times Uy makes it nonlinear. But these terms disappear in the steady state form, and we got rid of this with the penalty method, and there's our 2 equations. And we're going to solve the 2D Navier-Stokes equations in this funny looking region here. And on the bottom we're going to have a free flow boundary condition. On the sides we're going to have no flow boundary conditions. No flow just means U and V are zero, so that's like a sticky boundary where the can't cross the boundary, but it can't go parallel either. On the bottom we got free flow. That means that V can't be zero because it can't cross the boundary. This is a solid boundary here, so the fluid can't go perpendicular to the boundary anywhere. Here it can't go horizontally either, so the U and V are zero on all the boundary except the bottom, where we're going to have free flow conditions, which means V is zero here, the perpendicular velocity is zero, and U sub y is zero. U is not necessarily zero here, it is on the other parts, but it can flow, but U sub y is zero at the boundary. So on 4 pieces of the boundary, U and V are both zero, and that's easy. Those are just fixed boundaries. Our unknowns are both zero. On the bottom is a more complicated. On the bottom we said that V is zero, and therefore V sub x is zero. So if V is zero on the whole horizontal boundary, then V doesn't change with x, so V sub x is zero. And then we said the other boundary condition is U sub y is zero, so Uy plus Vx is zero. And the free boundary conditions for Galerkin method, which we have to use because of the geometry, it's not a simple region, is A1 times Nx plus B1 times Ny. But on the bottom, Nx is 0, Ny is minus 1. The unit normal is downward. So that's just 0 plus minus 1 times B1. B1 is that, and that's 0 because, as we said, V is 0. Therefore, V sub x is 0. U is not 0, but U sub y is 0. So GB1 is going to be 0. Now, on the other part of the boundary, that's we want V to be 0. We just said the fluid can't cross the boundary, so the vertical velocity is 0. So how do we? It's kind of a mixed boundary conditions. These are kind of a pain in the neck with Galerkin when you have basically one free and one fixed. You have to consider it to be free at positive arc numbers, and you just set GB2 equal to beta V, where beta is a real large number, and that forces V to be 0. So this will force V to be 0. That'll force Uy plus Vx to be 0. So GB1 be 0, GB2 will be a large number times V. That's the way you handle mixed boundary conditions with the Galerkin method, unfortunately. Okay, here we go. We don't want to work through a prepared example. Well, it's a two-dimensional problem. Have to use the Galerkin method because of the region. Double precision, yes. Parameters, there's the density, which problem says 1.1. There's the viscosity, which is, I'll call RMU for mu, 0.1. I think that's all. And the region is not simple. You can't write it as a function of P, X and Y as function of P and Q, so we're going to have to do it the hard way. However, I'm going to do it the easy way because I'm just going to read from the file pd2d.in that I prepared ahead with the 6 vertices and the 5 triangles. So I want option 3 the hard way, and then I input a pound sign and it'll start reading the, we'll show you the triangulation at the end when we run it. Any curve boundary? No. How many triangles we want in the final triangulation? Let's do 1,000. Let's use cubic elements, steady state, not linear. How many steps? Defaults to 15 Newton's methods. It's nonlinear, so it has to iterate Newton's method. We'll just use the default to 15. How many equations are there? There's 2. call the variables u and v, which are velocity, not displacement now. So remember, we got rid of this third equation by replacing pressure by this. So just these two equations. Is it symmetric? No. It's usually not worth trying to figure that out. Usually just say no. Okay, we do want an integral just to compare with the, we're going to do this two different ways, and we're going to compare, and I'm going to calculate the integral of u sub y minus v sub x, which is the vorticity. We'll see later what that is. No boundary integrals, no Dirac delta functions. Do you want to define some parameters? Yes, I want to define the pressure. Here's where we define the pressure to be minus, let's take 10 to the 5th power, 100,000 times ux plus vy. So that's where we define the penalty method parameter. It turns out it doesn't make too much difference what parameter we put there as long as it's a large number, except that you don't want to make it too large. If you make it, 10 to the 15th power, you're going to have round-off error problems. So anywhere between 10 to the 4th and 10 to the 10th will probably give the same results. So pressure is minus alpha times ux plus vy. And now, here's our equations. F is, we're going to take F1 on the left-hand side. Remember, F1 is y, F2 is minus x. Oh, I may not have told you that. There's a body force here. F1, F2, the vector F is going to be y comma minus x, which is basically just a fictitious body force that will cause the fluid to rotate. So I think I forgot to tell you that. But so this F1 is going to be y, F2 is minus x. I'm going to take it on the other side because this is going to be a1 sub x plus b1 sub y equals, the left-hand side will be F1, this F1. So F1 is going to be that. Remember, this is 0 here, so it's just, we want the density rho times ux plus v times uy minus F1, which was y. And A1 will be this here, 2 mu times ux, 2 times r mu times ux minus p, which was, alpha minus alpha ux plus vy. Notice there's no derivatives of p in here. A1 is just that minus p. And B1 is going to be mu times uy plus vx. That there. Next equation, F2 will be, that's 0, u v sub x plus v sub y minus F2. So that will be rho times u times vx plus v times vy minus F2, but F2 is minus x, so that's plus x. So there's a body force vector F, which is y minus x. That's a rotating force, so it's basically there's some kind of a whirlwind going on in there that's gonna, I just put that in to make it circulate. If that were 0, there'd be no movement at all. Okay, A2 then will be this thing, mu times uy plus vx, and B2 will be this thing, 2 mu times vy minus p. That takes care of the partial differential equations. Now, initial conditions, since it's nonlinear, you are asked to supply initial conditions. Those could be important if it's highly nonlinear, but for this problem, the rho, if rho is real large, it'll be highly nonlinear if the density is high, but it's not high enough. The 0, 0 turns out to be good enough initial starting values for this problem, so we don't have to worry about that. Fixed boundary conditions. Well, on the 4 of the sides, the well, we went by so fast with the reading from PD2day.in, but all of those were set to -1 arc because the U and V are both 0 there. So I can just say no, I don't have any fixed boundary conditions where the boundary conditions must be specified because they're both 0. If U or V were not 0 in that, I'd have to define them here, but the default is 0, 0, so just giving it a negative arc number automatically defaults them to 0, so I can say no, I don't have any negative arc numbers where I need to define the boundary conditions because the only negative arc numbers I have, the default will work. Now the free boundary conditions, yes, in the bottom, remember, that's down here on the bottom, and you have to, these free boundary conditions are a pain in the neck with Galerkin, but you just have to, be real careful. Follow the instructions. That's arc number 1. Positive arc numbers are free boundary conditions. And there, again, the boundary conditions are these, and we went through the analysis there. This is the A1 nx plus b1 times ny is equal to gb1, and we showed you why gb1 needs to be 0. And gb2 needs to be a large number times v, or PD2D, you can just say 0v, and basically that will be a large number of v, but the program will decide what reasonable large number is, so that saves you a little work there. That's the only free boundary, and we're almost done here. Now let's see, let's take a 20 by 20 output grid in the whole region, and I just want to do a vector plot of the velocity field uv, so it plots the, if I want to plot u comma v, I choose I var x and I var 1 to be 1 and 4. And let's make it undistorted. These are just scaling things. Okay, u comma v, and that's all we want. Okay, ready to run. And the Newton's method converges only 4 iterations, despite the fact that we just gave 0, 0 for u and v bound initial conditions. If they didn't converge, you'd want to give better initial conditions or something. And the integral of the vorticity is correct. It's supposed to be about very close to 0.7. So it seems to be working. So now let's look at the plots. There's the initial triangulation that we read from the file pd2d.in to save time. There were 6 vertices. I gave the coordinates of the vertices. 5 triangles. I gave the, for triangle 1, I said 1, 2, 6, and then the arc number is 1. So see, these 4 arcs are all -1. That's a fixed boundary because u and v are both 0 there. U and v are both given, and they default to 0, in fact. And then down here we had free boundary condition, which is basically mixed. V was 0, but then uy plus vx is 0, so we had to do the funny mixed boundary condition, but that was a positive arc. And there's the final triangulation of 1,000 triangles. And there's the fluid field, and since there was, remember on this, 4 sides, u and v are both 0. See, there's no free flow here. It's like a sticky boundary where u and v are both 0. Down here you have free flow. That means the fluid can slide along the boundary, but it can't cross the boundary. So everything looks like it ought to be, and it's swirling because of that body force, basically a swirling force. Now let's rerun this though with a higher density and see what happens. Something interesting will happen. So I'm going to edit the program to change the density, and I'm going to change it to let's just make that 11, 10 times bigger. And hopefully 0, 0 will still work. It might not. believe it will though. Initial conditions. It's more nonlinear now, and it seems to be working still. The integral of vorticity is different, but it's a different problem. I assume that's correct. And it still converges. And let's look at the velocity field again. Okay, now the velocity field looks different. But if you think about it, it's kind of what you'd expect. It's basically higher Reynolds number. That means that the density is higher or the velocity is higher. So think of this as if you had a higher velocity here. This is sort of what you'd expect. It's swirling around, and it, well, basically coming off of this corner, it goes more straight, whereas before it went on up there. Anyway, that's reasonable. Okay, now we're going to solve the same 2D problem in a totally different way using a stream function approach. Remember I said that the Navier-Stokes equation, this is the 2D version, and if those terms are zero, it's steady state. The 2D version, it's almost impossible to solve the way it stands here with the pressure, so you'd have to have three variables, u, v, and pressure. And there's no pressure in this equation, just first derivatives there, no boundary conditions on P. P is a problem. And we got rid of P with the penalty method by just replacing P by alpha times that, and that worked pretty good in 2 or 3 dimensions. Now what we're going to do is totally different to stream function approach. This only works in 2 dimensions. And but again, the idea is to get rid of the pressure, because the pressure is a problem here. And what we do is we define a stream function phi such that the velocity field is phi sub y minus phi sub x. If u and v satisfy the divergence equation, you can prove that there will exist such a stream function, but you can see that if u and v are equal to phi y minus phi x, then automatically the divergence equation is satisfied, because u sub x will be phi yx plus v sub y would be minus phi xy, which is 0. So that takes care of this equation automatically. The stream function does. And then we're going to define something called the vorticity as u sub y minus vx. And since u is phi y, u sub y is phi yy. And since v is minus phi x and minus vx is plus phi xx, so the vorticity is equal to the Laplacian of the stream function phi. And so that's one equation there. Just this definition of vorticity is going to be phi xx plus phi yy. Now, where does this other equation come from? Well, we take this first equation, we take the derivative of that with respect to y, take the derivative of this with respect to x and subtract, and the p's go out. So it's another way to get rid of the p. Take the first equation with respect to x minus second equation with respect to y, and you got pxy minus pyx. Totally gets rid of the pressure. And after simplifying, this sub y minus this sub x, you get the following in terms of the stream function phi and the vorticity omega. And notice we have 2 nice second order equations for the 2 variables omega and phi. And so that's what we want to solve. We got rid of the pressure, and we got rid of the divergence equation also, because it's automatically satisfied, and got rid of the pressure by, well, you saw how we got rid of that. So there's our 2 equations for the 2 unknowns phi and rho, phi and omega. And if you solve that, you'll get phi, and then the velocity field would just be phi sub y comma minus phi sub x. So we're going to solve those 2 equations now in that same region. Now, what about the boundary conditions? Well, again, we have, well, this is going to be 0 because we're going to look at steady state, so that term disappears, but not that term. And Rho is the density again, and that's the viscosity. So we're going to solve these two equations, but now the boundary conditions are a little confusing. So on the no-flow boundary, where u and v are both 0, what are the boundary conditions in terms of phi and omega? Well, if u and v are both 0 on a boundary, that means both derivatives of phi are 0. That means the gradient of phi is 0. That means that the derivative of phi in any direction is 0. So the parallel to the boundary direction is derivative is 0, and the normal derivative is 0. So you can take phi to be constant, namely we'll take it to be 0. So if you take phi to be 0 on the boundary and the normal derivative of phi to be 0, that assures that the derivative of phi in the tangential and the normal derivative direction are both 0, which means the gradient 0. So that's the fixed boundary, the no-flow boundary. So no-flow boundary, we have phi and the normal derivative of phi equal to 0. On the free-flow boundary, what have we got? Well, we've got, remember, v is 0, and that means that, well, on the bottom, let's just look at the bottom. This is going to work on other boundaries too, but on the bottom, remember, v is 0, and u sub y is 0. So if v is 0, that means phi sub x is 0, which means phi is constant along the boundary, and we can just take it to be 0. So we have phi equals 0 again there. And the vorticity is also going to be 0 on the bottom. Why? Because, remember, u sub y equals 0 is the other boundary condition, and v sub x, v is 0 along the entire boundary, the bottom boundary, so the horizontal derivative is 0. So both of these are 0, therefore omega, the vorticity is 0. So on the bottom, where we have free flow, phi and omega are both 0, which is a little ironic because basically that means that in terms of phi and omega, that's a fixed boundary. The free flow is fixed boundary because the vorticity and the stream function are both 0. On the rest of the boundary, where the no-flow boundary, that's actually going to be the more general boundary conditions because phi and normal derivative are 0. Okay, so we're going to solve the problem using the stream function approach now. No, don't want a prepared example. It's two-dimension. We're still using Galerkin method. Double precision. Okay, we still got the same two parameters. The density is going to be at least, it's going to be 1.1. And the viscosity 0.1. And again, the region is complicated, so we have to use the third option. And again, I don't want to input this, so I'm going to read it from the file. And it's essentially the same triangulation as the other problem, except that the arc numbers are reversed. The free boundary is now fixed, and the fixed boundary is now free. But I've got that in there now. No curve boundary, 1,000 triangles again. Steady state, not linear still. Might as well do 15. Okay, now we have two equations, but now the unknowns are not u and v, they're phi and omega, which I'll call w, so I'll call it phi hi and omega. Phi is the stream function, omega is the vorticity, and it's definitely not symmetric. Strongly recommended yes, so let's say yes. Now I want to calculate the integral of the vorticity. This time the vorticity is just w, but it should still be that 0.7, the same as we got with the penalty function approach. Don't want any boundary integrals, don't have any Dirac delta. So now I want to solve these two differential equations. I'm going to list this as my first equation. So that will be derivative respect to x of phi x plus derivative respect to y of phi y equals omega, or I'm calling it W. So F1 will just be W, A1 is phi X, B1 is phi Y. Now the next equation is first equation. A2 would just be mu times Wx, and B2 will be mu times Wy, and F will be everything on the left-hand side. Well, this term is 0 because it's steady state, but everything else here, so we have F2 will be rho times phi y times omega x minus phi x times omega y, plus, now remember F2 is minus x, so the derivative of minus x with respect to x is minus 1, and the derivative of F1, which is y, with respect to y is 1, so we just got minus 1 minus 1, so this is just going to be minus 2. And mu times Wx, derivative with respect to x, plus derivative with respect to y of mu times Wy, and that's our partial differential equations, and hopefully 0 initial conditions will be enough to make this converge. Okay, so we do have a fixed boundary, that's the bottom, where both variables are 0, but since they're both 0, I don't need to define them, I use the default. Now, free boundary condition, that's everything else. That's art number 1, and this time, again, we have to be careful. This is phi x times nx plus phi y times ny, and that's going to be 0 because remember, phi and normal derivative are 0, and this is the normal derivative, so we put in 0 to make the normal derivative 0, and we need to put a large number times phi, or just 0 of phi to make phi 0. So the first equation makes phi's normal derivative of phi, which is what this is. This is mu times the normal derivative of omega. It doesn't matter what it is because we're setting it equal to a large number times phi. So that should work. Anymore? No, they're all the same. Okay, now we're going to want to plot, remember the velocity. We want to plot the velocity. That's going to be, remember, phi y comma minus phi x. And so I'm going to have to define we haven't used these before. These are, if you want to output something other than the normal things, and we want to output phi y minus phi x. So phi y, I'm going to replace a1 by phi y. I'm going to replace b1 by minus phi x. That way when I ask for a plot, vector plot of a1 and b1, it will actually be the velocity. And 20 by 20 grid again. So let's do the vector field. And now the vector, as I said, I want it to be phi y comma minus phi x, but I've a1 and b1 now contain those, so I just say 2 and 3. Now I also want to do a contour plot of the string function, and you'll see why it's called the string function. So I want to do a contour plot of phi I var equal 1 is phi. And we're done. So let's try running that, and it should give a 0.7 again as the integral of vorticity. If it doesn't, it's not working right. Looks like it is working. So let's look at the plots. Here's the final triangulation. It's the same as before, except that now the free flow is a negative boundary condition because the two variables are given there, namely 0, and the fixed flow is the more general type boundary condition. There's the final triangulation of 1,000 triangles again. And there's the velocity field, phi y comma minus phi x, which is should be exactly the same, almost exactly the same as what we got the other time. And then let's look at the contour plot of phi. Those are the constant phi levels, and the flow follows the streams here. Well, it's shown in the book that the velocity phi y comma minus phi x is always going to be parallel to the constant phi curves. Well, you can see why that is. If this is a constant phi curve, then the gradient of phi is perpendicular to the curve. That's phi sub x comma phi sub y, and the velocity field is phi y comma minus phi x, so the dot product of the gradient phi x phi y and the velocity field phi y minus phi x is 0, which means that the velocity field is perpendicular to the normal to the curve, i.e. it's parallel to the curve. So the constant stream function basically shows the streams of the velocity field. Okay, we use the Galerkin method on both the penalty method and stream function approach. Collocation method works fine for the stream function approach, but that's only for 2D. For the penalty method, you can use collocation, and I do have a couple of problems, but it really doesn't work as well as the Galerkin method. And that means in 3 dimensions, where you have to use the penalty method and the collocation method, there are some difficulties, although there is a couple of problems in the text. They're 3-dimensional and they work reasonably well, but if you can use the Galerkin method, even though it's a little more complicated, the boundary conditions, that's to your advantage. Now, and in 3 dimensions, the boundary conditions are especially complicated, but it's all explained in the problems of what appropriate boundary conditions for free flow and no flow. We also derive the axisymmetric fluid flow equations, and again, it's a huge mess, but that means that your region has to be such that nothing depends on theta. You can switch to cylindrical coordinates RZ and theta, and there's no theta if everything's symmetric around the axis, in which case you can reduce the fluid flow problem to a 2-dimensional problem, and it looks like this. Again, it's not at all obvious where some of these terms come from. It's rather complicated, but there they are. There's the axisymmetric Navier-Stokes equations. This is the axisymmetric divergence equation. You'd think it'd just be UR plus WZ equals 0, but it's got this extra term and you've got these extra terms. And anyway, it's there and it's derived in another problem, but there's actually a problem where you solve the axisymmetric. And remember, the whole reason for using the axisymmetric equations is 2-dimension and therefore much simpler. In fact, you can use Galerkin method again. So here's a problem where you're supposed to use the axisymmetric equations, and here's the region. It's this is x is r and y is z. So basically this is r equals 0. So if you rotate this around the r equals 0 axis, it's kind of a notched cylinder with a circular notch here, and but so it's basically a 3D problem, but it's reduced to 2D problem by axisymmetry, and that makes it a whole lot easier.